Welcome back. The objectives of this particular lecture are to discuss estimation of steady state heat transfer rate through building walls or roofs, discuss estimation of overall heat transfer coefficient of different types of walls and roofs, then discuss governing equations for unsteady state heat transfer through building walls and roofs, and finally estimation of unsteady heat transfer rate to the conditioned space using CLTD or ETD values from tables. At the end of the lecture, you should be able to find steady state heat transfer rate through building walls and roofs, calculate overall heat transfer coefficients of different types of walls, write governing equations for unsteady state heat transfer through building walls and roofs, and finally estimate unsteady heat transfer rate to the conditioned space using CLTD or ETD values from the tables. Let me give a brief introduction to heat transfer through building structures. Due to temperature difference between indoor and outdoors, heat transfer takes place through the walls and roof of the building. This type of heat transfer is known as fabric heat gain or loss. If the building is gaining heat, you call it as heat gain. If it is losing heat, you call it as fabric heat loss. The fabric heat gain or loss is sensible heat transfer. That means it does not involve any latent heat transfer process. And the exact analysis of buildings to estimate fabric heat transfer is very complicated because of the fact that the outdoor and indoor conditions change continuously, and buildings are of diverse shape and orientation, and a wide variety of materials are used in construction. So, because of these factors, exact analysis of buildings is very difficult. First, let us look at one-dimensional steady state heat transfer through buildings. Heat transfer through the building is assumed to be steady if the indoor and outdoor conditions do not vary with time. So, these are the assumptions under which you can apply one-dimensional steady state heat transfer through the buildings. First requirement is that the outdoor and indoor conditions should not vary with time. And the heat transfer is assumed to be one-dimensional if the thickness of the building wall is small compared to the other two dimensions. That means the wall thickness is small compared to its width and height. Then you can treat it as a one-dimensional steady state heat conduction problem. In general, all building walls are multi-layered and non-homogeneous and could be non-isotropic also. First, let us look at homogeneous walls, then we shall discuss non-homogeneous walls. So, a homogeneous wall is subjected to radiation and convection heat transfer on both sides, while heat transfer through the wall is by conduction. So, let me show a picture of this. So, this is a homogeneous wall. Okay, so this is the wall, and these are the outdoors, and this is the indoors. And just for an example, let us assume that the outdoor temperature T0 is greater than indoor temperature Ti. Okay, and you have outdoor surface. I mean, the outer surface of the wall is subjected to radiation heat transfer, and it is also subjected to convective heat transfer. So, heat transfer takes place from the outdoor to the outer surface of the wall by radiation and by convection. Then heat transfer through the wall takes place by conduction. Then heat transfer from the wall to the indoors from the inner surface of the wall takes place again by radiation and by convection. Okay, and since we are talking about steady state heat transfer problem, whatever heat enters the wall from the outside should be equal to heat leaving the wall from the inner surface. Okay, so heat transfer at the outer surface is always equal to heat transfer to the from the inner surface. Okay, that is why it is steady state. Now, the heat transfer rate per unit area of the wall under steady state is given by Q subscript in is equal to Q subscript CO plus Q subscript RO, which is equal to Q subscript CI plus Q subscript RI. What is Q subscript CO? Q subscript CO is nothing but the convective heat transfer from the outdoor air to the outer surface of the wall, and Q subscript RO is the radiative heat transfer from the outer surface to the outer surface, and QCI is a convective heat transfer from the inner surface to the conditioned space, and QRI is the radiant heat transfer from the inner surface to the conditioned space. By linearizing the radiative heat transfer coefficient, we can write the heat transfer rate as Q in is equal to H0 into T0 minus TWO, which is equal to Hi into TWI minus Ti, where Hi and H naught are inner and outer surface conductances. Okay, so these are this is known as outer surface conductance, and this is known as inner surface conductance. And T naught and Ti are the outer and inner dry bulb temperatures, and T subscript Wo and T subscript Wi are the temperatures of the outer surface of the wall and inner surface of the wall respectively. And from the resistance network, the surface conductances Hi and H naught are given by, let me show the resistance network here. Okay, so this again show the wall, and as I have mentioned, this is the outer surface of the wall, and here you have radiation and you also have convection. Okay, so and these two heat transfer modes take place parallelly. Okay, so you have one parallel path by which radiation is taking place and another path through which convection is taking place. So radiation is taking place from a radiant source at temperature TSO, and convection is taking place from the outdoor dry bulb temperature T subscript O, and 1 by HRO, this is your radiative resistance to radiative heat transfer, and this is the resistance to convective heat transfer on the outer surface side. And through the wall the heat transfer is by conduction, so this is the conduction resistance, where delta X is thickness of the wall and Kw is the thermal conductivity of the wall material. And again from the inner surface to the conditioned space, that means to the indoors, you have heat transfer by radiation and convection. So you have radiation heat transfer and convection heat transfer. So you can see here that again 1 by H subscript Ri is the resistance to radiation heat transfer inside the conditioned space, and this is the resistance to convective heat transfer. Okay, so now we can write an equivalent circuit by combining these two parallel resistances into a single resistance 1 by H naught, and similarly for the inside surface side we can combine these two resistances into a single resistance 1 by Hi. So this H naught and Hi are the equivalent resistances which consider both radiation as well as convection heat transfer on the outer surface side as well as on the inner surface side. So you can easily show from the network that H subscript I, that is the inner surface conductance, is equal to H subscript Ci plus H subscript Ri into Twi minus Tsi divided by Twi minus Ti. Okay, where as I said this is your inner convective heat transfer coefficient, this is the inner linearized radiative heat transfer coefficient, this is the temperature of the wall on the inner side, and this is the temperature of the conditioned space, surface temperature of the conditioned space. Okay, so this is the dry bulb temperature of the conditioned space. Similarly for the outside surface conductance, you can write an equation of which is of the similar form, and you can see here that if for example if the inside surface temperature is same as the inside dry bulb temperature, then Hi is simply equal to Hci plus Hri. Similarly for the outside, if the outside surface temperature T subscript So is equal to outdoor dry bulb air temperature, then you will find that H naught is equal to simply Hco plus Hro. Assuming inside air to be still, normally in the conditioned space we have to maintain very low temperatures, very low air velocities to avoid the problem of draft. So typically the air velocities are of the order of 0.15 to about 0.25 meter per second. So for all practical purposes you can treat air inside a conditioned space to be still air. So if the air is still air, then the heat transfer between the air and the surface will be because of natural convection. Okay, so if you want to estimate the convective heat transfer coefficient in the condition inside the conditioned space, you have to apply suitable natural convective heat transfer correlations. Okay, a simple correlation is given here. For example, H subscript Ci is the natural convection heat transfer coefficient inside the conditioned space. This is equal to 1.42 multiplied by delta T by L to the power of 1 by 4, where delta T is the temperature difference between the surface and the air, and L is the length or height of the surface. Okay, so this is generally valid for atmospheric air. Okay, so if you know the surface temperature and the air temperature and the dimensions of the wall, you can calculate the heat transfer coefficient. And as far as the outside heat transfer coefficient is concerned, normally due to wind speed, the heat transfer from the outside air to the outer surface of the wall is by force convection. Okay, so hence one has to use suitable force convection heat transfer correlations to estimate HCO. Okay, so you have to use if it is a horizontal wall, then you have to use force convection heat transfer coefficient for flow over a horizontal wall, like that. And the linearized radiative heat transfer coefficient HR is calculated from the equation. This we have discussed while discussing fundamentals of heat transfer. The linearized heat transfer coefficient HR. Okay, so this is equal given by this expression, where T1 and T2 are the two surface temperatures between which radiation heat transfer is taking place, and epsilon is the absorptivity of the wall, and this sigma is the Stefan-Boltzmann constant, right, and the temperature should be in absolute scale. Okay, and typical values of inner and outer surface conductances have been estimated for different conditions of air motion, direction of heat transfer, orientation of the surface, and emissivity of the surface. Let me show you some typical values. Okay, so this table shows, as I said, surface conductance values in watt per meter square Kelvin for different orientations, okay, different air velocities and surface emissivity. For example, take this. This orientation of the surface is horizontal, and the air velocity is still air. That means you can apply this still air condition to the conditioned space inside the building. Okay, and if the direction of the heat flow is upwards, and if the surface emissivity is 0.9, then the heat transfer coefficient is 9.4 watt per meter square Kelvin. If the surface emissivity is 0.7, then heat transfer coefficient is 5.2 watt per meter square Kelvin, and if the emissivity is 0.5, this is the heat transfer coefficient. What do you mean by horizontal and direction of heat flow is up? You have a wall like this. Okay, this is a horizontal wall, right, and you have air here, and the direction of heat transfer is upward. That means heat transfer is taking place from the air to the wall in this direction, okay, where the gravity is in this direction. Okay, for this condition you can take these values, and as I said, epsilon is the emissivity of this surface. Okay, and for the next condition, again you have the still air, and the direction of heat flow is downwards. That means you have again the wall. Okay, and let us say that air is here, and heat transfer is taking place from the wall to the air, okay, in this direction. Okay, and G is acting in this direction, in downwards direction. Again, for different values of surface emissivity, you have the values of heat transfer coefficient. Okay, next comes vertical wall and still air. That means you have a vertical wall like this, okay, and you have air, and heat transfer is taking place between the wall to the air. Okay, and again, if the emissivity is 0.9, this is the heat transfer coefficient. If the emissivity is 0.7, this is the heat transfer coefficient, and for 0.5 emissivity, this is the heat transfer coefficient. Okay, so as I said, these three conditions are applicable for the conditioned space, that means inside the building. Okay, and next two conditions where the air velocity is given as 3.7 meter per second and 6.4 meter per second. Here this is applicable to any position, because here the heat transfer rate is mainly by force convection. Okay, one thing you can notice here is that when the air is still, for example for these conditions, heat transfer rate is by natural convection and also by radiation. So emissivity is coming into picture. Okay, and typically the heat transfer coefficient values are small, right, because the convective heat transfer coefficient is generally small in case of natural convection. Whereas when you have force convection, that means when you have velocity of air at the rate of 3.7 meter per second or 6.4 meter per second, heat transfer is mainly by force convection. When it is by force convection, the orientation of the surface is not very important. Okay, similarly the emissivity of the surface is also not very important, because compared to the force convection heat transfer, the radiation heat transfer is negligible. So you can see that for this case, the heat transfer coefficient depends only on the velocity. If the velocity is 3.7 meter per second, then the heat transfer coefficient is 23.3 watt per meter square Kelvin. If it is 6.4 meter per second, it is 35 watt per meter square Kelvin. Okay, so these are the typical values. In the absence of any correlations or any better data, you can use this data for estimating the inside and outside surface conductances. You must keep in your mind that the surface conductance includes both convective as well as radiative heat transfer coefficients. Okay. Now you can eliminate the surface temperature of the wall, that means T subscript Wi and T subscript Wo, and write the steady state heat transfer equation in this form using the overall heat transfer coefficient U. Okay, if you are using overall heat transfer coefficient U, you can write the steady state heat transfer rate per unit area. This is heat flux basically, watt per meter square. That is equal to overall heat transfer coefficient multiplied by the temperature difference between the outdoor air and indoor air. Okay, T naught minus Ti. So U is nothing but 1 by total resistance, right? So this is nothing but all the resistances are summed up. Okay, and the inverse of the resistance is your overall heat transfer coefficient. Okay, and we have seen that the expression for overall heat transfer coefficient for this homogeneous wall is given by this. This is the resistance, inner convective and radiative resistance. This is the resistance offered by the wall. This is outer convective and radiative resistance. These three resistances are in series, so you add them up, find out the R total, and the inverse of R total will give you the value of U. Okay, once you know the value of U and outer and inner dry temperatures, you can calculate what is the steady state heat transfer rate. Now let us look at non-homogeneous walls. Buildings may consist of non-homogeneous materials such as hollow bricks. The hollow bricks are quite very widely used in buildings, because hollow bricks have better insulation properties compared to solid bricks. Okay, that is the reason why hollow bricks are quite widely used. So heat transfer through materials such as hollow bricks involves simultaneous heat transfer by convection, conduction and radiation. So let me show a picture of hollow brick. Okay, so this shows a picture of a hollow brick. So you can see here that in this case heat transfer takes place by conduction here, okay, through the material of the wall. This is by conduction heat transfer through the solid material, and through the air space you have heat transfer taking place by radiation as well as convection as well as conduction. Okay, so you have a multimode heat transfer problem here. Okay, conduction, convection and radiation. Okay. So for such problems, what is done is all these effects like convection, conduction and radiation, they are lumped into a single parameter, and this single parameter is called as thermal conductance C, and the heat flux through the hollow brick is simply given as Q is equal to C into TWO minus TWI, where TWO and TWI are the outer and inner surface temperatures of the hollow brick, and C is the conductance. The heat transfer properties of common building materials have been measured and they are available in tabular form. Okay, let me show typical values. You can see here that for a wide variety of commonly used materials, you have the properties. For example, for bricks, okay, again under bricks you have common brick, you have face brick, you have fire brick. So for all these types of bricks, these are the specific heat values. These are the densities, and these are the thermal conductivity values. Since these materials are homogeneous materials, you need not give conductance value, thermal conductivity value is enough, and from the thickness of the brick and the thermal conductivity you can find out what is the resistance. Next comes woods. So you have plywood, hardwood, softwood, and these are the specific heat values, these are the densities. Again these are the thermal conductivity values, because these are also homogeneous. When it comes to hollow clay tiles or hollow concrete blocks, the thermal conductivity values are not given, because here the heat transfer rate, as I have discussed just now, is by multimode, convection, conduction and radiation. So for these materials the conductance values are given. These values are generally obtained from experimental measurements. So for different types of, for example, hollow concrete block of 10 centimeter thick, this is your conductance value. For 20 centimeter thick, this is a conductance value. For 30 centimeter, that is a conductance value. Similarly for foam concrete, okay, this is the density value and this is the thermal conductivity value. Similarly for glass and similarly for insulating material. Okay, so these kind of properties are available in air conditioning design data books such as ASHRAE data books or other air conditioning books. So looking at the tables, you can take the properties like specific heat, density, thermal conductivity or conductance, and you can calculate, if for example if you are calculating the overall heat transfer coefficient, then you can use either the conductance value or the thermal conductivity and thickness, and you can find out what is the overall heat transfer coefficient, and from the overall heat transfer coefficient and the temperature difference you can find out what is the heat flux through the wall. Okay. Now let us look at air spaces. What is air space? Buildings may consist of air spaces between walls, and air spaces may also be there, for example in the false ceiling or in attic space. Okay. And since air is a bad conductor of heat, the air space provides effective insulation against heat transfer. So, this is one of the reasons why air spaces are used in buildings. Okay, it provides good insulation against heat transfer, so the load on the building gets reduced. And heat transfer through the air space takes place by a combined mechanism of conduction, convection and radiation. So, again you have a multimode heat transfer in an air space. Okay, so let me explain that. So, you have this is a wall and this is a wall, and in between these two walls you have the air space. Okay, so this is the air space. Let us say that this surface is at a temperature T1 and this surface is at temperature T2. Okay, and for the time being let us assume that T1 is greater than T2. Okay. So, heat transfer takes place from this surface to this surface. So, since you have air here, so heat transfer takes place by conduction through the air, by convection from the surface to the air and from the air to the surface, and directly by radiation from this surface to this surface. So, you have all three heat transfer modes taking place between one surface to the other surface through the air film. So, this is the air gap. Okay. So, for this kind of air spaces, how do we calculate the heat transfer rate? Now, heat transfer rate through the air spaces depends upon its width, orientation and surface emissivities, because radiation is involved. So, surface emissivities also come into picture, and also the temperature difference between the two surfaces. When the air gap is more than 2 centimeters, it is observed that the conduction heat transfer is negligible, and generally the convection and radiation are the major modes by which heat is transferred. Okay, when the gap is more than 2 centimeters. And the heat transfer rate through air spaces is given in terms of, again we use conductance. Okay, so heat transfer rate Q is equal to C into T1 minus T2 per unit area, so watt per meter square, where C is the conductance of the air gap and T1 and T2 are the two surface temperatures. And assuming heat transfer coefficient Hc to be same for both the surfaces. Okay, so what is the meaning of that? So, you have two surfaces. Okay, this is surface 1 and this is surface 2, let us say. So, you have air here. So, there is a heat transfer coefficient between this surface and air, and there is heat transfer coefficient between this surface and air. So, if you assume that this heat transfer coefficient between the air and surface 1 and air and surface 2 are same, okay, which is equal to Hc, right, and the temperature is uniform, that means there is no temperature gradient inside the air space, right, and these two plates are infinite parallel planes, then the conductance is given by C is equal to Hc by 2 plus Hr. You can derive this very easily, this expression under these assumptions. Okay. So, the conductance value can be obtained if you know the convective heat transfer coefficient and linearized radiative heat transfer coefficient. And the linearized radiative heat transfer coefficient is given by this expression, where F subscript 1 2, this one, this is called as view factor. Okay, view factor or configuration factor or geometry factor. Okay, this we have discussed again while discussing radiation heat transfer. So, you can see that the view factor is a function of emissivity of surface 1 epsilon 1 and emissivity of surface 2 epsilon 2. So, if you know the emissivity of the surfaces 1 and 2, you can calculate the view factor, and if you know the surface temperatures T1 and T2, you can calculate radiative heat transfer coefficient, and if you can calculate the convective heat transfer coefficient, you can find out what is the conductance of the air space. Okay. And again typical conductance values of air spaces are given in this table. Okay, so these are the typical conductance values of air spaces. Again you can see here that since you have convection as well as radiation, the orientation plays a major role, because inside the air space convection heat transfer is by natural convection. So, the orientation and temperature difference become important. For example, for horizontal air space, that means you have air space like this. Okay. So, this is your air space. Okay, and if the heat transfer is upward, that means heat transfer is taking place from the bottom surface to the top surface, and if the air gap, that means this gap is 2.1 centimeters, this is the conductance value. If it is 11.6 centimeters, the conductance value is 6.2. On the other hand, for the temperature difference of 10 degree centigrade, that means T1 minus T2 of 10 degree centigrade, if the heat flow direction is downwards, that means you have two surfaces like this and heat is flowing in this direction. Then for different air gaps, you have the conductance values 5.7, 5.1, 4.8, okay, these things. And for vertical, that means you have surfaces like this, okay, and the temperature difference between these two surfaces is 10 degrees, and the heat flow is in the horizontal direction, that means in this direction. Then depending upon the air gap, you have the conductance values 5.8, 5.84, air gap of 2.1 and 11.6 centimeters. Okay, similarly for 32 degrees centigrade, these are the conductance values, and if it is vertical, these are the conductance values. In general, you can see that when the temperature difference increases, the conductance value increases. Okay. Now let us look at a combined wall, a multi-layered composite wall. So in general, a building wall or roof consists of layers of homogeneous and non-homogeneous wall materials and air spaces. That means the same wall may consist of several layers. One layer may consist of a homogeneous material, second layer may consist of a non-homogeneous material, third layer may consist of an air space, and so on. Okay, so this kind of a wall is known as a composite wall or a multi-layered wall. So for a composite wall or multi-layered wall, the heat transfer rate per unit area or the heat flux is given by Q subscript in. Okay, so this is equal to overall heat transfer coefficient U into temperature difference across the wall T naught minus Ti. Okay, T naught is the outdoor temperature, Ti is the indoor temperature. Okay, which is equal to T naught minus Ti by R total, where R total is the total resistance to heat transfer. So total resistance to heat transfer for a multi-layered composite wall is given by this expression. Here this factor 1 by H subscript I is the internal resistance due to inner conductance, and this factor sigma I is 1 to n delta x by kwi is the sum total of the conduction resistances offered by all the homogeneous walls. Okay, so this holds for all homogeneous walls, and this one takes care of all non-homogeneous walls as well as air spaces. Okay, and finally 1 by H naught, this takes care of the outer resistance. Okay, outer resistance due to conduction and convection and radiation. Okay, so if you know the individual resistances, or if you know the properties of the individual materials, right, then you can calculate the individual resistance, and from the individual resistances you can calculate the total resistance, and from the total resistance you can calculate the overall heat transfer coefficient, and from the overall heat transfer coefficient and temperature difference you can find out what is the steady state heat transfer rate through a multi-layered or composite wall. Sometimes a multi-layered or composite wall may have parallel paths. Okay, then you have to draw a equivalent resistance network, and from the resistance network find out what is the total resistance, and from the total resistance find the overall heat transfer coefficient, and so on. Okay, so it is always very useful to draw the resistance network first and then evaluate each individual resistance and then add them up and find the total resistance. Okay, that way you can find out the heat transfer rate under steady state conditions. Okay. Now let us look at unsteady state heat transfer through walls and roofs. In general, heat transfer through building walls and roof is unsteady due to variation in solar radiation and varying temperatures. Even though we have discussed, so far we have discussed steady state heat transfer and how to calculate heat transfer rate under steady state condition, you find that most of the times the heat transfer is not under steady state. Okay, most of the times heat transfer through the buildings is in an unsteady state. Okay, this is mainly because of the variations in the solar radiation and variations in the outdoor and indoor temperatures. If the building is air conditioned, then the indoor temperature may remain constant, but the outdoor temperature will vary continuously throughout the day, and again it will vary from day to day, right. Similarly, the solar radiation varies throughout the day. So because the variation of the solar radiation and outdoor temperature with time, you have a problem where the heat transfer is not steady but it is unsteady. Okay, here the unsteady state arises because of the time varying boundary conditions, and also because of the thermal storage properties of the walls and roof. Okay, in general the building walls and roofs have very large but finite thermal capacity. Okay, because the thermal capacity, they store energy, and similarly they release energy. So this thermal storage effect gives rise to unsteady effects. Okay. For example, let me show a solar radiation and how the solar radiation varies. Okay, so this is a typical variation of direct, diffuse and total radiation intensity on a horizontal roof under clear sky conditions, and the data is for holds good for Kolkata, and the day is June 21st. Okay, it's a horizontal roof under clear sky conditions. So you can see that it is 0 from in these points it is 0 because this is before sunrise and this is after sunset. So solar radiation will be there only during the sun, okay, during the day. So at this point sun rises, so gradually the diffuse radiation and direct radiation increase with solar time. They reach a peak at solar noon, okay, then again they gradually decrease and again they become 0 at sunset. So it is 0 at sunrise and 0 at sunset. So it is continuously varying throughout the day. Because of this, the outdoor boundary condition, the radiative boundary condition also varies continuously, right, with time. Similar to solar radiation, the outdoor temperature also varies with time. As I said, due to large but finite thermal capacity of the building walls and roofs, under unsteady conditions at any instant the heat transfer rate at the outer surface is not equal to the heat transfer rate at the inner surface. This is very important. What it means is, if you have the wall, let us say, okay, this is outdoor, okay, this is indoor. So heat transfer is taking place to the outer surface of the wall by radiation, okay, and also by convection, let us say. Similarly, heat transfer is taking place from the inner surface of the wall by radiation and convection. You find that whatever heat transfer is taking place here, okay, is not same as whatever heat transfer is taking place from inner surface to the conditioned space. That means if here if this is Q in and if this is Q out, then Q in is not equal to Q out. Okay, this comes into a picture because of the thermal storage capacity of the walls. Okay, and what we do here is, for the sake of simplicity, we assume one dimensional heat transfer, and we also assume that the temperature of the conditioned space remains constant. That means typically we are carrying out this analysis for a building which is air conditioned, because it is possible to maintain the conditioned space temperature at a constant value only by using an artificial method such as an air conditioning system. Okay, if you do not have any air conditioning, then inside temperature also will vary along with the outside temperature. Okay, so for the sake of simplicity, we assume that the building is air conditioned, so inside temperature remains constant, whereas the outside temperature, that means surface temperature on the outer wall, varies continuously. Okay. Now what we do is we apply energy balance equation to the outer surface of the wall at any instance of time theta. Okay, so let us take the outer surface of the wall. Okay, so this is your wall and this is the outer surface. Okay, so this outer surface is shown by this dashed line, and we apply energy balance to the outer surface. So energy balance to the outer surface, since surface does not have any mass, whatever energy enters the surface must leave the surface. What is the energy entering the surface? Energy is entering the surface by way of direct radiation, okay, I subscript capital D multiplied by alpha D, where alpha D is your absorptivity of the surface for direct radiation and ID is the intensity of direct radiation. Similarly, you also have radiation reaching the surface because of diffuse radiation. So I subscript small d is the diffuse radiation and alpha subscript small d is the absorptivity for diffuse radiation. And heat transfer also takes place from the outdoor air to the outer surface of the wall by convection. So you also have convective heat transfer, and heat transfer may also take place by long wave radiation, either from the wall to the surrounding surfaces or from the surrounding surfaces to the wall, that is given by this R. Okay, so these are all the heat transfer rates from the outside to the surface of the wall, and this should be equal to the heat transfer from the surface to the wall. Okay, that is given by, okay, since if you are assuming that heat transfer through the wall is by conduction, this should be equal to Q at x is equal to L. L increases, x increases in this direction, and the thickness of the wall, let us say that thickness of the wall is L. When x is 0, that means the inner surface of the wall, x is L means outer surface of the wall. So Q subscript x is L is equal to sum total of all these things, that should be equal to minus k wall, okay, let me write here, minus k wall dou T by dou x at x is equal to L, where this is the conductive heat transfer from the outer surface of the wall to the wall. Okay. So this is the heat balance equation for the outer surface, that is what is shown here. Q at x is equal to L and any theta is equal to minus kW dou T by dou x. This is nothing but your Fourier's law of heat conduction, which is equal to heat transfer by convection, heat transfer by direct radiation, diffuse radiation and long wave radiation. Okay, so this is the energy balance for outer surface. Similarly, you can write an energy balance for the inner surface. Inner surface does not have any solar radiation, so you do not have these terms are not there. So simply whatever heat is transferred from the inner surface is because of combined effects of convection and internal radiations which are clubbed in Hi. So that is equal to minus kW dou T by dou x at x is equal to 0 and theta, which is equal to Hi into Tx is equal to 0 minus Ti. Okay, and as I said, due to because of the capacitive effect of the wall, Q at x is equal to L and theta is not equal to Q at x is equal to 0 and theta. That means Q in is not equal to Q out. Okay, and ultimately what is the load on the building? Load on the building is nothing but what is the heat transferred from the wall to the conditioned space, that is given by this. So this is very important as far as the building cooling load is concerned. Okay. Now for building load calculations, we need to know the heat transfer rate at x is equal to 0. As I have already explained to you, we need to know what is the heat transfer rate from the inner surface of the wall to the conditioned space. That means from x is equal to 0 to the conditioned space. This requires information regarding temperature distribution inside the wall. That means we need to know how the temperature distribution is there inside the wall, that is dou T by dou x, because the heat transfer to the conditioned space, as I have said, is given by this expression minus kW dou T by dou x at x is equal to 0. So if you know T as a function of x, okay, then you can find out dou T by dou x at any theta, okay, taking the value of x as 0. So from this you can find out this parameter. Okay, so how do we find the temperature distribution inside the wall? As I said, for the sake of simplicity, let us assume that the wall is a homogeneous wall. Okay, if the wall is homogeneous, then heat transfer is by conduction. Okay, so if you want to find out what is the heat transfer, what is the temperature distribution inside the wall, you have to solve the conduction unsteady state conduction equation. Okay, and for a plane wall, we are talking about plane wall. For the plane wall, the unsteady state heat conduction equation is given by this partial differential equation. PD is the partial differential equation. Dou square T by dou x square is equal to 1 by alpha dou T by dou theta, where T, as you know, is the temperature, x is the space coordinate, theta is the time coordinate, and alpha, as you know, is the thermal diffusivity of the wall. That is, alpha is equal to K wall divided by rho wall into Cp wall. Okay, K is the thermal conductivity, rho is the density of the wall, and Cp is the specific heat of the wall. So this is the equation that governs the heat conduction equation through the wall under unsteady state conditions. Okay, so we have to solve this equation. You can see that this is a partial differential equation and it is second order in space and first order in time. So you have to specify two boundary conditions for space and one boundary condition for time. Okay, if you want to solve the equation. And the solution of the PDE is subjected to the following initial and boundary conditions. As I said, you have to specify these conditions, only then you can solve the equation. So this is your initial condition. That means at some theta, arbitrary value of time, theta is 0, the temperature distribution inside the wall is given by this, and we should know this. That means this is known. Okay, and this is specified as known boundary condition for time or an initial condition. Okay, then you have to specify two boundary conditions because you have dou square T by dou x square term. So the two boundary conditions are for the inner surface, that is x is equal to 0. One boundary condition is this minus kW dou T by dou x at x is equal to 0 into theta is Hi into Tx is equal to 0 minus Ti. This is the boundary condition at the inner surface. Similarly, the boundary condition at the outer surface, that is my x is equal to L, is given by this. Okay, Q x is equal to L theta is minus kW dou T by dou x at x is equal to L theta, which is equal to the heat transfer rate by convection, heat transfer rate by direct radiation, heat transfer rate by diffuse radiation. This is the long wave radiation, right? What is done here is the boundary condition at the outer surface, that means this one is written in terms of an effective or equivalent temperature called as sole air temperature. Okay, this is known as the sole air temperature. So what we do is we club all these factors and we write this boundary condition also similar to this boundary condition by introducing a fictitious equivalent temperature called as T Soleil temperature. And if you compare these two equations, you find that the Soleil temperature T subscript Soleil is given by T subscript O, which is the dryable temperature of outdoor air, plus this factor. Okay. So you can see that when there is no radiation, that means when there is no direct radiation, when there is no diffuse radiation, when there is no long wave radiation, Soleil temperature is simply equal to outdoor dry bulb temperature of the air. Okay. On the other hand, when you have radiation, when you have sun, you may have solar direct radiation, you will have diffuse radiation, then the Soleil temperature can be much higher than the outdoor dry bulb temperature. Okay. And during the night, this will be 0 and this will be 0, whereas this can be positive, then it is possible that the Soleil temperature can be smaller than the outdoor dry bulb air temperature. And you can also see here that the Soleil temperature also depends upon the outdoor surface conductance H0. Okay. So the advantage of defining a Soleil temperature is that you can write the outdoor boundary condition also as H0 into T Soleil minus T wall temperature. Okay, so the form looks simple, but the Soleil temperature depends upon several factors like the radiation, solar geometry, and outdoor convection and all that. Okay. The governing heat, now how do we solve? Now we have defined the governing equation as we have seen for a simple plane wall, okay, plane homogeneous wall. The governing equation is a partial differential equation, and let us say that we have also specified the required initial and boundary conditions. So the problem is fully defined. Now the question is, how do we solve it? You can solve this governing differential equation either by using an analytical method, or by using numerical methods, or by using empirical methods. So what are the typical characteristics of these methods? Analytical methods are used for simple geometries with simple boundary conditions. Okay, simple geometries means you have a plane wall. Okay, simple boundary conditions means outside temperature or outside radiation varies as a simple harmonic. Okay, for this kind of simple geometries and simple boundary conditions, you can derive an analytical expression, or you can get an analytical solution. Okay. Whereas the numerical methods are very powerful and they can tackle complex geometries with any boundary condition. So this is the advantage of numerical methods. You can use the numerical methods for any type of any shape of the building or for any type of boundary conditions. Okay. However, numerical methods are in general more time consuming, and the accuracy also, they are not 100% accurate, unlike analytical methods. And based on the form suggested by analytical methods, the heat transfer rate to the condition space at any time theta can be written as, so this, as I said, this is the form suggested by the analytical method. Okay, by the analytical method, you can write at any time the heat transfer rate to the condition space, that is Q x is equal to 0 and theta, this is the heat transfer rate to the condition space, as I have said. That is equal to UA, where U is the overall heat transfer coefficient of the wall, A is the surface area of the wall, multiplied by T sol air subscript m minus Ti plus UA into lambda into T sol air theta minus phi minus T sol air subscript m. So what are all these things? This one, T sol air subscript m, is what is known as mean solar temperature. Let us say that you find the mean solar temperature for the 24 hours. You calculate the hourly solar temperature and find an average of that. So that is the mean solar temperature, T sol air subscript m. Okay. Then Ti is the temperature of the condition space, which we are assuming to be constant, right? And this lambda, okay, is what is known as decrement factor. Right, I will explain what it is, and then this phi is what is known as time lag factor. Okay, and here T sol air, look at this temperature. What is this? I am calculating heat transfer rate at some time theta. Okay, so this is written as in terms of temperature at time theta minus phi. Okay, where phi is the time lag. That means let us say that I am calculating heat transfer rate at 6 p.m. okay, on a particular wall. I want to know what is the heat transfer rate from the wall to the conditioned space at 6 p.m. and let the wall has a time lag of 5 hours. Okay, then T solar subscript theta minus phi is the temperature of the wall or the solar temperature of the wall at 6 minus 5, that is 1 p.m. Okay, so that is the meaning of theta minus phi. Okay. And now coming to decrement factor. What is the decrement factor? Due to the large but finite thermal capacity of the wall, the heat transferred to the conditioned space is less than the heat transfer to the outer surface of the wall. Okay, as I have already explained to you, because of the thermal capacity of the wall, Q in is not equal to Q out, and it may so happen that Q in is much larger than the Q out. So this introduces a factor called as decrement factor. Okay, similarly you have what is known as the time lag factor. And what is the time lag factor? The time lag is the difference between the time at which the outer surface receives heat and the time at which the inner surface senses it. So let me give an example. Let us say that you have a wall here. Okay, let us say that this is a wall and this is the outdoor and this is the indoor. Let us say that suddenly this wall experiences some heat transfer. Okay, let us say that at this time, let us say time is 4 p.m. Okay, at 4 p.m. this wall, so outer surface of the wall is suddenly exposed to some heat transfer Q in. Okay, and because of the thermal capacity of the wall, you find that the inner surface doesn't sense this immediately. Okay, some time is required for the inner surface to sense this heat transfer, and let us say that if the time lag is 3 hours, okay, then you will find that this inner surface senses this heat transfer at 4 plus 3, that is 7 p.m. Okay, so this is what is known as time lag. This is the reason why if the outside temperature is maximum, say at 3 p.m, we find that the indoor temperature in an unconditioned room is maximum at say 7 p.m. or 8 p.m. Okay, for example, at mid noon at 12 o'clock, outside may be the hottest, but inside the room temperature will be very high, not at 12 o'clock, but maybe at 3 o'clock or 4 o'clock. Okay, so this is because of the thermal capacity of the wall. Okay, and this factor is known as time lag factor, right? And the decrement and time lag factors depend on the thermal capacity of the wall. Obviously, what is the thermal capacity of the wall? The thermal capacity of the wall depends upon the density of the wall, thickness of the wall, and specific heat of the wall. Thicker walls with large thermal capacity have small decrement factor and large time lag, and vice versa. Okay, so let me show that variation of decrement and time lag factor. This graph here shows the decrement factor as a function of wall thickness. Okay, these are calculated for building material having a specific heat of 840 joule per kg Kelvin. Okay, so you can see that the decrement factor is 1 when the thickness is 0. Okay, that means there is no wall, and the decrement factor is 1, and as the wall thickness increases, the decrement factor reduces. Okay, so in general the decrement factor varies between 0 to 1. Okay, thicker walls have lower decrement factors, thinner walls have higher decrement factors. Okay, next this graph shows the variation of time lag with wall thickness, and for different types of walls having different densities. Okay, so you can see that as the wall thickness increases, the time lag increases. Okay, for example, for 450 mm thick wall, the time lag could be 15 hours. Okay, similarly for 150 mm wall, the time lag is 5 hours, like that. Okay. As heat transfer to the conditioned space depends on time decrement and time lag, it varies with thermal capacity of the wall. Okay, so obviously the heat transfer rate, as we have seen, depends upon the solar temperature, which in turn depends upon the decrement and time lag factor, and decrement and time lag factor depend upon the thermal capacity of the wall. So finally you find that the heat transfer to the conditioned space depends among other factors on the thermal capacity of the wall. Okay, so let me show a typical variation of heat transfer rate. Okay, this graph here shows the heat transferred to the conditioned space. Okay, not heat flux, but total heat transfer to the conditioned space as a function of solar time. Okay, for a thin wall a thick wall, okay, and a thicker wall. So you can see that the heat transfer rate increases from about 8 am, that means slightly 1 or 2 hours after the sunrise. For a thin wall, the heat transfer rate increases in this manner, and it reaches a peak at about 4 pm, and then again it starts decreasing, okay, and it reaches a minimum at about 8 am. Okay, and for a thick wall, again it starts increasing from about 8 am. It reaches a peak, you can see that around at midnight, okay, not during the daytime but during the night time, and again it decreases. And for a still thicker wall, you find that the peak heat transfer rate takes place not during the daytime at all, but it takes place at about 4 am, that means in the morning. Okay, so this is the effect of the thickness of the wall on the heat transfer to the conditioned space at different times. And you can also see that the total heat transfer rate, that is nothing but the area under this curve, is much higher for the thin wall compared to the thick wall. Okay, so one thing is that the peak heat transfer rate for the thin wall is very high, and the total heat transfer rate for the thin wall is also high compared to the thick walls. So since the peak heat transfer rate and the total heat transfer to the conditioned space are smaller for thick walled buildings, the required cooling capacity of the system will be less for thick walled buildings, so it is an advantage. And energy required for the air conditioning system is also less for thick walled buildings. Okay, so this is also an advantage. And you will find that if the wall is sufficiently thick, then it is possible to maintain reasonably comfortable temperatures inside buildings even without any artificial air conditioning systems, okay, because of the small decrement factor and large time lag. In fact, this is the principle behind the old temples and old forts or old buildings which have very thick walls. Okay, you find that these buildings even without any air conditioning are very comfortable even during peak summer. Okay, so this is because of the large thermal capacity of the building, which introduces small decrement factor and a large time lag. Okay. And now let us look at empirical methods for cooling load estimation. Heat transfer rate to the conditioned space can be written as we have seen by this expression. Okay, and this is written in terms of UA into some delta T effective, where this delta T effective is called as equivalent temperature difference ETD or cooling load temperature difference CLTD. And from this expression you can easily find that the equivalent temperature difference or cooling load temperature difference is given by this expression. So it includes the mean solar temperature, the time lag and the decrement, and it also includes the inside temperature. Okay, so all these factors are included. So you can find that the ETD or CLTD depends on decrement and time lag factors, solar radiation and ambient temperatures through solar temperature, and inside temperature Ti. Okay, and tables of ETD and CLTD have been prepared for fixed values of inside and outside temperatures. For example, they are available in ASHRAE handbooks for different latitudes, orientations, and different types of walls and roofs. Okay, so let me show typical tables. Okay, so this is the CLTD table for a flat roof without suspended ceilings, and this is taken from ASHRAE handbooks. And here you have 4 different types of roofs, 3, 4, 5, 6, and the description of the roofs are given here. Type 3 is 100 mm thick lightweight concrete, type 4 is 150 mm thick lightweight concrete, type 5 is 100 mm thick heavyweight concrete, type 6 is roof terrace system, and the properties are given here: mass per unit area, okay, and the heat capacity, and the CLTD values are given as function of solar time. You can see that for this wall, for example type 3 wall, at 7 solar time minus 2 is the CLTD value. At 8 am this is 1 degree, at 9 am this is 5 degrees, and this is at 10 am 11 degrees, like that. Okay, similarly for different types of roofs at different solar times. And this table gives the CLTD values for vertical D-type wall. Okay, and the description of the D-type wall is given. D-type wall means 100 mm face brick with 200 mm concrete block and interior finish, or 100 mm face brick and 100 mm concrete block with interior finish. Since it is a vertical wall, the orientation comes into picture, whether it is north facing or northeast facing, right? This is north facing, northeast facing, east facing, southeast facing, like that. Okay, and at different solar times, right? So these are the temperatures in Kelvin. And you can also see here the maximum CLTD value. For example, for east facing wall, 18 degrees Kelvin is the maximum CLTD, and for southeast wall also it is 18 degrees, and for the west facing wall it is 23 degrees, like that. Okay. So this kind of tables are available in ASHRAE handbooks. Now what is the validity of ASHRAE handbooks? The ASHRAE handbooks have ASHRAE tables have been obtained for inside temperature of 25 degrees centigrade and maximum outside temperature of 35 degrees centigrade with an average value of 29 degrees centigrade and a daily range of 12 degrees centigrade. What is daily range? Daily range means maximum outdoor temperature minus minimum outdoor temperature. Okay, so that value is taken as 12 degrees centigrade. Now for inside and average outside temperatures other than the above, the following adjustment has to be made to CLTD values obtained from ASHRAE tables. Okay, so if your values are different, for example, the inside temperature is not 25 degrees but something else. Okay, similarly the outside temperature, average temperature not 29 but let us say 32. Then you have to make an adjustment to the values obtained from the table. That adjustment is given by this equation. The adjusted CLTD values is equal to tabular values plus 25 minus Ti plus T average minus 29. So as I said, let us say that your Ti value is 25, then this adjustment will not be there. But if the average temperature is higher than 29, then you have to add that to the value that you obtain from the table. Okay, so that's how you get the adjusted CLTD values. Okay. And solar, this data is also applicable to solar radiation typical of July 21st at 40 degree north latitude. But in the absence of more accurate data, the tables can be used without significant error for 0 degrees to 50 degrees north latitude for summer months. Okay. And data is also available for other types of walls and roofs and for different latitudes. And adjustments are also suggested for walls and roofs with insulation, wetted roofs, etc. Okay. So if you look at the ASHRAE handbooks or other air conditioning handbooks, all these tables are given, either CLTD tables. If you look at other handbooks, they give what is known as effective temperature difference tables. Okay, as a function of the type of the wall, orientation, solar time, and all that for a fixed conditions. And they also suggest adjustments for other conditions. Okay, so if you have the tables and your specific conditions, then you can get the tabular value, apply the adjustment and get the adjusted value of CLTD or ETD. Okay, that one must use for calculating the heat transfer rate. Okay. And thus from the knowledge of CLTD or ETD, overall heat transfer coefficient and area of the wall or roof, one can easily calculate the heat transfer rate of the conditioned space as Q in is equal to UA into CLTD or UA into ETD. So CLTD value get from the table, U value calculate from the specification of the wall, and A is the surface area of the wall. Okay. Now the empirical methods based on CLTD or ETD are widely used by air conditioning engineers. However, since these methods are subjected to several limitations, a safety factor is always assumed to account for these. Okay, so they are not 100% accurate, all these empirical methods. So to take care of this, a safety factor is always assumed. More accurate estimates can be made by using numerical methods, which however are time consuming and expensive. Okay, if your building is having a different shape, or if you want more accurate results, you have to apply the numerical methods. So numerical methods, the advantage is that you can take care of any shape or any boundary condition, but the problem is that they are expensive and they are also time consuming. So that is the reason why most of the time the air conditioning engineers use the empirical methods and provide a safety factor to take care of the inaccuracies. Okay. So at this point I end this lecture, and in the next lecture I shall discuss the actual estimation of cooling loads on the buildings. Thank you.